Il fatto di registrare va ancora più lento il computer. Vabbè. Ce ne faremo una ragione. Un minutino, aspettiamo, poi partiamo. Vabbè, una vedete che non c'era. Una sta arrivando, gli altri due non lo so. Forse segue online? Non so. Vabbè, comunque. Vabbè, partiamo, basta. Questo. Okay, so let's start. You connected remotely. Can you hear my voice?
Professor, I can hear you very well.
Okay, perfect. So let's start with this lecture. Okay, so today we will start with something about machine learning. So just a brief summary of our previous talk, where we discussed about the possibility of using some deterministic approach to find defects starting from thermography. So from the theory, we know that the expected dependence in a logarithmic scale is something linear. And if there's a defect, maybe there's a change in your profile. This means that we can use the goodness of your linear fit as an indicator of your structure, of the presence of some defects. And we can use this coefficient of determination, R squared, which is somehow related to a kind of probability that we have something inside the material or not. So if it is 1, maybe it is completely sound, perfectly homogeneous, or if it is lower than 0, this means that your linear fit, your linear model is no longer valid, and maybe there's a defect. But there are many problems, so we have already seen that maybe we need something different, a more sophisticated approach, making use, for example, of machine learning. We have defined also a use case, the inspection of this calibrated plate made of glass fiber, reinforced polymer, made of some flat bottom holes, and we can see, we can imagine that these flat bottom holes are somehow related to a variation of your thickness, a local variation of thickness. So we can also give some semantics to our ground truth and say that where it is blue, our region of interest, we are in a sound region, and then the first line of defects is of surface defects, and then another line of in-depth defects. So this is our use case. So a brief introduction on machine learning. As I said in the first lecture, this is the, let's say, official definition of machine learning made by Herbert Simon where learning is any process by which a system can improve its performance from some experience. So typically in programming, you get that your computer, your machine, takes as an input the data and the program, which is the code that you have written on in your programming language, and produce, according to this code, an output. In machine learning, there's a switch between the output and the program. So the computer receives the data and the expected output to produce in some way, let's say a program. So let's say a model that is able to link the data, the input, and the output. And in any case, we can define some performance metric and a task, T, and experience, which is the input data set that we already know. And we will use it for training, but also for testing our machine learning-based application. Why we need machine learning? I think that this is a kind of question that you already can answer. Maybe for developing some systems where you can automatically adapt and customize your application to some need, to a personal need. For example, this is for personal news or for mail filtering, for detecting spam mails and so on. But also, the second point is a point that is related to the process of data mining. So once you have very huge data set, maybe you can find some correlations between inputs that you didn't discover so far. For example, this is the diapers and the beer is a typical example. So there are in the early 90s, there was a study that made a correlation between diapers and beer in the market basket. So when you buy some diaper, maybe you have in your own basket also some beer. And it's something that is typically, we cannot imagine how it is possible, but that's the truth. Or there's the need for make some ability to reproduce your way of thinking with artificial intelligence. So let's say that you want to recognize some written character. This is a typical example, and you are training your model to work with written characters and then to understand it, to translate it in ASCII code. Or develop some system that is too difficult. So you don't know how to inspect, for example, let's say in quality control, you don't know how you can derive your physics of your problem, and then you want to train some model to make the work for you. Why it is possible now? First of all, there are many, many available data. So this is the first point. So now we are in the internet era, and typically you can manage lots of inputs, lots of data. And then also there's this is the last point, there's an increase in support from companies, from industries. So there's no reason for some jealousy, let's say, of the data if somebody can solve your problem. Now we are in the era of the open data, open science, open software, open everything. And there's another point that is the increasing computational power. Maybe you know that training a network, a deep network, for example, can be very, very costly in terms of CPU requirements. And then with the availability of GPUs, of graphical processing units, you can handle many, many cores for training your network, taking advantage, as I said, of the numbers of the cores that you get. In your graphical card, you have many cores, and you can use these cores for training your network. So when you read the news that Elon Musk has bought 1,000 GPU cards is because you want to implement artificial intelligence in Twitter. So there's a need. So if you want to train something, maybe it's better to shift your processing on graphical cards. And this is done in many programming language for free, even in MATLAB, but also in Python and other language programming. And there's also a growing progress, of course, in available algorithms. Although we should think that many the very preliminary works have been already done in the 70s. But because there were no available data, there were no available resources, these were just theoretical studies. But now today we can implement it. So there's a growing process in making new algorithms, new networks. And when do we need to use machine learning? For example, when there's no expertise of the domain. Let's say, for example, a path planning procedure for a rover that has to travel on Mars. Maybe we don't know the terrain or the landscape that we are going to encounter, and you can create your machine learning algorithm to cope with this kind of problem. Or humans cannot explain their expertise. Let's say for speech recognition, so you hopefully are understanding what I'm saying, but you don't know how it is possible. How can you convert a wave signal, like my voice, in something that has a content, an informative content? Or you need to customize your model, let's say in personal medicine, or you have very, very huge amounts of data. This is something related to data mining. Once you get lots of data, maybe you are not able to find the best correlations between objects because you are driven by your expertise, but maybe there's something else to be discovered. Some histories, they started in the 50s, but as I told you before, the first actual implementation of neural networks were in the 60s with the perception, that is the basic neural network, or with pattern recognition tasks. Then these first preliminary studies were, as I told you before, more oriented to theoretical development. So the first implementations are of the 80s, 90s. For example, in 90s, there were the first implementation of reinforcement learning approaches. And we will see very briefly what is reinforcement learning. But now with having the possibility of using these GPUs and whatever, there are many advances in machine learning from, for example, in the early 2000s, support virtual machine or graphical models, but also transfer learning. That is what we already talked about. So take some knowledge from a domain, from a large domain, and then put this knowledge in a very specific domain, but taking advantage of what you have already learned before. Or for mail management, or in learning with robotics, with the vision. So why vision in these years? Because there were the availability of digital cameras that previously were not so available. And now deep learning systems, learning for big data, Bayesian method that means implementing also probability measurements, or application to vision, speech, social networks, human-machine interaction. And for example, human-machine interaction in this group also include natural language processing. So this ChatGPT, the way of chatting with some bot that is answering to your question in a natural way. And then, who knows? Possible applications. There are many possible applications, and we will use it in manufacturing quality control, but nothing precludes your use of machine learning to your research domain, to your favorite area. State of some brief words about the state of the art. So you know that there's the possibility of creating autonomous cars. There are many works also in Italy. For example, in Modena, they have in Modena, Parma, Reggio Emilia, they have created some autonomous car that is able to capture images from the environment and then recognize signals, recognize the path or the pedestrians and make some autonomous navigation. But also in unstructured domains. So go back to Mars, let's say. So look at the vision with the vision to the map, to your terrain, and make some path planning according to the optimization of a cost function. Let's say in Mars discovers, maybe you are more interested in reduce the battery power required for your path. Maybe the shortest path is not the best for battery requirements. And you can also use this information, this optimization, this model function to define something different. Or this is something related to the problem of segmentation that is now currently at the state of the art. So taking some pictures of, let's say, in this case, a 3D vision image of panoramic vision of your environment and identify for any point, make a classification and say that there's a car, there's a building, there's a window, there's a pedestrian, there's the road. Or another typical speech recognition system are those for other machine learning application are those for speech recognition, where you have your waveform as an input, then you extract some feature, and using some neural network, create a new representation of your input features, and with the decoder, you are decoding this representation of your input signal is something that has a meaning. And this is what is done, for example, on your smartphone, when you use your voice to write down some text. So it's not local, but you need to be connected to some server that is acquiring your voice and then translate your voice to text. Or there are many types of learning. So the first one is supervised learning. So in supervised learning, you are assuming that you have some training data. And of course, there are also labels that are associated to your training data. So you know almost everything of your data set. So you know that if you have, in our case, for example, it could be seen as a problem of supervised learning because we have a calibrated specimen and we have for each point of our surface, we know perfectly if it belongs to something that is really some region or is a definitive region. Unsupervised learning is different, not so different, but where you have training data, but you don't have any target output. So you are working with a data set that is not labeled. And we will see also how to approach to these kinds of problem. Semi-supervised learning is in the middle between supervised and unsupervised learning. In semi-supervised learning, you have a training data with only few examples. So you have, for let's say, 1,000 images, but of these images, you have labeled only 10 images. Maybe you can use these 10 images to acquire some knowledge and then export this knowledge to the remaining images. This is a problem of semi-supervised learning. In reinforcement learning, you don't have a data set, but the inputs are given to your network, to your model in time, and you create the rewards for a sequence of actions. For example, this video that you can see here is an example of reinforcement learning. So this is taken from YouTube, and the authors of this let's say joke, but it's an important application of reinforcement learning, are not playing. So there's a machine intelligence, machine learning algorithm that has been trained by the experience. So when Super Mario loses his play, they can learn from this experience and make the second attempt, tentative to complete the level. So this is completely automatic, made by reinforcement learning. There is something that you typically do, for example, in gaming, let's say. And we can also represent these types of, so reinforcement learning is something that we will not discuss in this course. Also, semi-supervised learning is something that we will not discuss here, but we will focus our attention more on supervised learning and unsupervised learning. Let's say that you have a feature space in 2 dimensions. So just to make it representable. Let's say that you have a 3-class problem. For example, we have pressure and humidity of the air, and then we want to classify a problem if it is raining, it is not raining, or it's about to rain. It's about raining. So let's say that red dots is not raining. Green, it's about to rain, and then these blue crosses it's raining. So the meaning is it's raining. So you get your features, and you can plot your points in this 2D space and say that all the points that are red are examples of one class, and then all the stars are examples on another class, and the crosses examples of the 3rd class. In supervised learning, you can imagine that your problem is the definition of these lines to separate your clusters, and then you know that all the inputs into the 2D space that, for example, are in this region belongs to a class of red. That means it's not raining. Once you get your pressure and humidity values. So you train from your data, and then you test it from something that is not given in your data set. So in supervised learning, you know the meaning of any clusters. In unsupervised learning, let's say that you get these inputs, but you don't know nothing at all about the meaning of these points. Maybe the best way is to cluster these points, let's say in groups, and then this is cluster number 1, this is cluster number 2, and cluster number 3. You don't even have a meaning associated to your cluster. Maybe there's somebody that is more expert that can give a meaning to these points, but you can also try to create a model that, and for any time you get a new observation of your phenomena that belongs to cluster 1, you will label this phenomenon as the result of cluster 1. We don't know that is not raining, but you can group it and say this is cluster 1. So this is the difference between supervised and unsupervised learning. In semi-supervised learning is a kind of mix between the two different learning. For example, and what we can see here, how we can see that using semi-supervised learning, although you get the input that are colored, that are labeled, you have many other examples that are not labeled. So instead of having lines, perfect lines, you can define something, a separation, which is made by a curve. Because there are other points that are not labeled, but that change your line separation like this, making it or as a curve. And let's focus on supervised and unsupervised learning. Again, in supervised learning, you get your input, which is your training inputs. There are text, documents, images, sounds, signals, multimodal signals, point clouds, your specific input. Then you extract these feature vectors, where features are some characteristics, discriminant characteristics of your phenomena. And then you can give these features, feature vectors, and the labels to your machine learning algorithm, which is able to make a model. And then for any new data that has not a label for sure, you can again define your feature vectors in the same way that you have defined in training and make a prediction with your model to get some expected label. In unsupervised learning, it's almost the same. So you even define your features, but you don't have the labels. So you can create your model and again, clusterize in terms of the most likely clusters related to the input that you have created, or the cluster that get the best representation of your input features. Input features in the previous examples, where for example the humidity and the pressure. So you don't need other features because maybe for your problem state, if it is raining, these two features are enough. Maybe you don't need temperature or the time or other features because these are meaningless for your representation. So these are the features of my problem. So I can state if it is raining, just taking account pressure and air pressure and air humidity. So there's another difference that I want to show you between classification and regression. So in our problem of detecting the defects, classify the defects, we are talking about classification. So in any case, you get some couple of input and output, where inputs are in the form of vectors, feature vectors, and then the output is something. If this something is categorical, so this is a problem of classification. Is raining, is not raining, is about rain, and or any other problem. For example, in our case, sound region, defective region, in-depth defect, and so on. But if the output is a real value, this is a problem of regression. In our case, for example, instead of classify groups or classes and say surface defect, in-depth defect, maybe we can use something different. For example, try to estimate the depth of the defect with a real number. This is a problem of regression. So in this examples. Let's say that you have the information about a tumor size, and you want to discriminate between something that is good and something that is not. You can state, for example, that this line makes your best prediction. So, but here we are defining a problem of classification. So there are some category, good or not. In regression, let's say that you want, for example, let's say that you know that there's a problem that could be fit by a linear regression. So any other, so once you get your input, you can estimate your output in a linear way, and then you're making some regression. Even if your input has a noise, you can have your estimation of your predictor output. So these are some points that are also always valid. So what we need for designing a learning system. So we need, first of all, to choose the training experience. So this means that you should have your data set. So, and your data set must be representative of your problem, of course. If it's not, your model cannot predict something that is not possible. You cannot predict if it's raining by taking the temperature and time. Then you should know a target function. So a target function, for example, could be the error in your prediction that you can define in many ways. And how to represent your target function. So how you can represent your function that you want to optimize to get the best performance with your model. And then, of course, try to choose the best learning algorithm that can optimize this target function starting from your experience. So as I told you many times, there's a difference between the training and test set. So once you have your data set, maybe it is better to make a split between the training set and the test set. So the training is made of examples that are used for defining the numbers that are within your architecture. So you define your architecture, your model, and then this model is empty of any number. You use your training data for having numbers. So to make a mathematical representation of your model. The test set should be something different from the training set, and you use your test data to test the performance. Of course, training and test should be somehow linked. This means that you are, let's say that you are training your model with for the estimation of for classifying if it is raining or not, with some data set that is taken here in Italy, and then you want to test it with another data set taken from Pakistan. Maybe these are not similar, and your results will be not so good as expected. So test and training should be on the same, let's say, on the same scale. If it is not, you will require transfer learning. So you need to retrain your model with the new data, with a new data set, to take into account the possible variabilities that you get due to the change of your data set. You can even predict with the same model if it is raining or not in Pakistan, but maybe you should retrain your your network to fine-tune the numbers that are inside. And this is the problem of transfer learning. So in practice, this is let's say, a very high-level loop. You should understand your domain and define your goals. Then make some analysis of the data, selection of the data, cleaning, pre-processing. So try to help your model to solve the problem, giving him the best data you can. Then learn the model by training. Try to interpret your results, and if these are not so good, try to understand why there's a problem. Then consolidate your discovered knowledge, and if it is not enough to solve your problem, again, make a loop and start again from understanding your domain and try to have a deeper insight into your problem. So I think that this is valid for any research activity, but in machine learning is even more important. So the evaluation, as I told you before, training set is made for create your model, and then you should evaluate your performance. So you have a test set that it can be represented in the same feature space that you have defined before for the training. So you take your data, you transform it in your feature vectors that are on the same representation space of the feature vectors of the training, make your prediction, and of course, try to understand if you are working good. How you can do that? Using the metrics that we have already seen in the last lectures. For example, these are the formulations for a binary classification. Let's say that you get, so in this table, which is also known as confusion matrix. So your actual class is yes or not. And these are your predictions. So if you get some example, so we are testing, so we are in the test data set. But you can also do the same for the training. But of course, okay, now we will spend some few words about this. If both are yes, you are predicting well. This is a true positive, the same as a true negative, where you predict both. So you expected something that is no, and you predict as no. Then there's a false negative or a false positive, depending on which is your prediction, knowing your expected value. The accuracy is the summation of the truth divided by positive and negatives, divided by all the elements of your test set. Precision and recall, and we already discussed it. So precision is picking randomly some example of the test set. You can say which is the probability that this result is relevant for you. Or again, for recall, picking randomly an example, so this is a more related to sensitivity, if your relevant document is retrieved or not. As I told you before, you can estimate in this accuracy, precision, recall, all the metrics, also in the training set. If your training set has, let's say, an accuracy of 90%, and then the test set has an accuracy of 90%, maybe you're working fine. But let's say that you have a training set that is performing with an accuracy of 50%. Okay, you can say, maybe my model is not able to generalize the problem to the new data. But if also your training finished and did with an accuracy of 50%, is not the problem of the data that are different, but it is a problem that your model was not so complex, was not able to solve your problem. So was not too, let's say, smart to to understand which are the phenomena that are involved in your process. And even in training, you are not able to converge on a good accuracy. Okay, so training accuracy, precision, recall, any metrics are useful to understand if your model is enough for solving your problem. But the test is even more important because you want to understand if your model that you're trained on some data can be generalized to any other data that has the same form of your test of your training set, but of course is different, has never been given as an input to your model. Okay. And this is a problem of generalization. So you will say, okay, let's make the most complex model in the history to solve the training, to have the best training, to have an accuracy in my training of 100%. So let's make a very easy example. So we are taking just two features, and we are representing this, the input in our two feature. So in the previous example where humidity and pressure. And you get this this scatter plot of your region. Maybe you can make a decision boundary like this, a line, which is a very simple decision boundary. Or you can create a much more complex model that is not making a complex linear decision boundary, but something like this made of segments to include all the points, except this one, all the points in your training. So here you get almost 100% of accuracy in training. Not 100% because there's this point here that is not included. Here maybe your accuracy in training is not, or 100% is lower. But in your opinion, which is the best? Maybe it's better to get something simpler, like this linear decision boundary, because maybe this is too much in love with your training data. And once you get something that is slightly different from your training data, it is not working at all. This is the typical problem of overfitting, an overfitting problem. So your model is not able to generalize because it is too much complex and is capable of solving only the examples of the training set. This is another example for regression. Let's say that you have you want to, very easily, you want to make a regression of these points that are some measurement of, I don't know which kind of physical variable. Let's say that is temperature in time. And this is a simple model, and is the most complex model. So this is a linear model where you are making a linear regression. In this case, you're using a higher order polynomial regression. Let's say that you have a new point, for example, here because of your noise. If you take this point here, maybe you get a residual, a difference with your model that is much lower than what you can expect by placing your point here, where your residual is higher, much higher, because your model is too complex and is perfectly representing your points of the training set, but is not able to make some generalization. Even in this case, we have made an overfitting. Let's say that we can also plot the problem of overfitting. So let's say that you have defined some metrics to understand which is your error. For example, in linear regression, we can assume that this error is the sum of the square residuals of the new point of the new estimated point with the actual one. You are improving your complexity, and your error on training data, of course, is going to decrease till be something like 0, as in this case. Here, your error is higher than your error that you can have with this higher order polynomial. So you're increasing your model complexity, your training error is going to vanish. On the test data, you get the opposite. So once you increase your model complexity, your error on the test data is going to be higher. So this region is a region of overfitting. This region on the left, of course, is a region of underfitting, where your model is not so good to understand, to interpret the input, and is not able to produce the data. For example, instead of using a linear model like this, let's say that we use y equal to b. Your model will be a flat line, and in this case, you get underfitting, because you are not able to represent neither during training nor during test to represent your model to get accurate results. So how we can compare, for example, models? As I told you before, once you get your full data set, you can split it, divide it in training data and test data. Typically, training data are in number higher than test data. So you need more training data than test, because you want to make the best training, and then you will estimate on a lower number of examples. Typically, 70%, 75% of your data set is used for training, and the remaining 30%, 25% for testing your data. And then you can estimate your accuracy on the test data. This is what we have seen till now. But you can also use another technique for making it. So you don't even know if your accuracy is good, because your test data were you were so lucky that you select randomly your test data to get the best result. And this is possible, of course. For example, in the problem of regression, if you have that your test data is something like here, maybe you get the very, very accurate results because of how you pick your test input. How you can manage this problem? Maybe making a key-fold cross-validation. So you take your data set and you divide it in k partitions. You use one partition as a test and the others for training. And make your first analysis. You train your data on the training set and then test your model on the test data, and you get some test performance. Then, in the second case, this is made k times, you change your training data. Instead of using the same as before, you use, for example, the first and the third. In this case, this k is equal to 3, okay? And you use your training data, your new training data, and you test your model on test data that are different from the previous one. Okay, then you can make it k times, and finally decide for the model that has, for example, the best the best performance on the test, or the best performance on the training. So it's up to you which is the best that you will consider. So this is a key fault cross-validation. There's another point. Key fault cross-validation can also be applied differently. For example, you get your whole data set and you preliminarily divide it in training data and test data. Okay, 75% of training and 25% of test. Then take your training data and divide it again, creating a validation set and a training data set. And you will try to make your model on the training set and estimate the performance on a validation set during training. Everything is performed during training. Your validation set will be used for early stopping. So if your training data are if your training is giving you, for example, an accuracy of 100%, but your validation set is not giving an accuracy of 100%, of 60%, maybe you are making some overfitting. Okay. The question is, the validation set is made of, the validation set is made of the training data. So you do the same of the full data set, splitting it in training and test, but once you have divided your test data and training data, you made a k-fold cross-validation on the training set, not on the whole data set. Okay, so you should imagine that you have two different phases of your process with machine learning. The first phase where you train your model, and another one when you test it. During training, you are also testing. And this is used for making a validation set that is not used for tune the parameters of your network. It's the same of a test set, but is used to stop your training. So, which is the problem? That when you get, so we need to decide when we should stop our training. So that's the point. If we go on with our training for 3 days, maybe at the end of your convergence, you get 100% of accuracy of your training. That's the truth. But you are in the case of overfitting, because then if you test your data that are here, your red is something apart, taken apart, you will get 30% of accuracy. So instead of making your training for 3 days, you want to stop it before to make something simpler. Okay. How we can decide when it's time to stop? Making a test during the training. If your validation set has some performance that are going to be too low, maybe it's time to stop. If your validation set is no longer improving performance, it's time to stop. Even if in your training you will go farther and farther and obtain even better results. Okay, so this is used for stop your training. So you use key-fold cross-validation during training instead during test. And okay, that is the point. So let's talk about the feature extraction. Okay. Sì.
avrà, non so, un tot numero di dati. Su ciascun dato va effettuato il ground truth e comparato all'esito.
The question was, what if you want to have your performance for the test data set, how you can estimate your performance? You should have your ground truth, even for the test. And for, let's say that you are making a model for classifying the images. And you want to estimate the performance of your model in testing something that is new. Of course, there should be a ground truth even for these images to get the estimation of the performance. In computer science, let's go back here. Your data set is full. You get 1 million images that you want to classify. You typically split before making your model these images that are all labeled. You split your images in the training set and in the test set. So even your test set has the labels in order to get the comparison of the models that you have produced. So let's go with feature extraction. In machine learning, let's say that you have a signal, maybe, and you want to classify this signal. Let's say that I have a temperature behavior in time, and given this temperature, I want to estimate if this signal belongs to a class of a sound region or a defective class. Okay. You can use your signal as it is as an input for your machine learning tool. But this is not the best way to work with machine learning. You should down the size of your signal. Instead of having the whole signal made, let's say, of 2000 samples, you should just take 10, 15, 20 features that are able to characterize perfectly your input and in order to be classified by the machine learning tool. So these 15, 20 numbers that are assuming everything, the contribution of the whole signals are the features. These features should be informative, should be discriminating, because of course you will not say if it is raining or not taking the temperature. Maybe you should have something that is discriminative for your problem. Should be independent. Maybe, let's say, I don't know how many features for our problem of the weather are dependent, but maybe you will not use time and the solar light as input features, because maybe these are related each other, because during night your brightness should be 0. Okay, so these are dependent and you should not take these features. Should be independent and in the correct number. Correct means as low as possible. Okay. In machine learning, which are the features? It's up to you. So if your problem is a specific problem, you should select the feature because you are the expert of the domain and you should be able to define your features. But there are many ways to define other kinds of features that are useful for other domains. For example, image processing, there are many features that you can use for solving your problem. But then you should select the best one for your specific domain, given your inputs. And some examples. Let's say character recognition. For example, let's say that we have some don't know if possible to, let's open my whiteboard. Just a moment, let's open again this one. Okay, let's say that this is our image, and this is the number that I'm writing. Okay, an image is a matrix of pixels, so we can divide it like this. And once this is black, let's say that I'm coloring, so in black and white. So this is 0, and this is 1. Okay, for any of the points that are under my sign. So this is a cross, but let's say like this. So actually, what you have is this. This should be 6. Which are the features that you can use, for example? Let's say an histogram of the ones that you have for along the lines and along your columns. So here, 2, 1, 2, 2, 3, 0. This is a vector, and I can create another vector here, 3, 4, 3, 0. I can then concatenate them and make the final vector. This could be a feature vector, okay, for my problem. Or maybe I can also add other features to this vector. Let's say the number of voids in my character. For example, here, this is 1. Or the number of stroke that I made for write down the number, just 1. Maybe if I made 7, there were 2 strokes. This could be a discriminant feature also. These are all the features that you can extract from, let's say, an image like this for character recognition. Or speech recognition. Let's say that you have a waveform that is my vowel or I don't know, whatever. For example, your feature could be the length, the power, the magnitude, the envelope of the magnitude, the frequencies, some response to a filter that I designed. This could be features for speech recognition. Let's say in a spam detection algorithm. So you get your mail and you want to say if this is spam or not. Maybe the language could be a feature. Maybe the number of people that are receiving this mail could be a feature. Or some specific word like password or I don't know, bank transfer. Maybe this could be a spam. Or in computer vision, there are many possible features. So computer vision, of course, includes character recognition, and there are many possible features. So many of them are already known in the literature, and you can take advantage of this. But if you have a problem where you are the expert, maybe you can define your own features. That will be, let's say, and we will see something about this, instead of using general features, you can use the parameters of a model, the theoretical model that probably could represent your problem. Okay. For example, image processing, boundary descriptor. So this is a typical example, a chain code. So here we get, this is an end character, 0, maybe, or a no, or I don't know. And instead of using the histogram or I don't know, and so on, you start from top left, Let me open the presentation. Duplicate. You can start top left and then see how this snake evolves. When it goes on the right, it is associated to a code that is 0, and this is a map of continuity, let's say. So 0, 0, top down, right down 7, 7, left down 5, and create, instead of using the whole image, create and chain code. Or you can make a skeleton-based feature. So you represent this rectangle with the line inside the rectangle. And once you get, for example, an L, you will get that this line is different. Or some histogram-based. So let's see, you can evaluate the energy of your image, the entropy of your image, many formulations that you can use for your image as a feature. Or texture feature, for example, this is a universal taxon dictionary where you get an histogram that is able to represent in a good way different textures that you have in your image. If you have, for example, let's say this texture and the histogram should be like this, if you have an anomaly, for example, some dots are connected, maybe there's a peak in your histogram different from what expected. So you are representing in some way your problem, in a different way your problem. Other features, for example, the histogram of oriented gradients. This is very often used in computer vision. So you create a model of what you want to find in your image, and then you compare it with these features, with this histogram-oriented gradient. So you take your image, you resize it to this size of 128, 64 pixels, and then you consider a block of 3 pixels, 3 by 3 pixels, square block, and compute your gradients along the 2 directions, vertical and horizontal. Once you get this representation of the gradients, you can also create with this formulation a magnitude of the gradient and the angle of the gradient. So to understand which is the direction and the magnitude of the gradient, of the changes within the images. So this is the point. The gradient is higher where you have an edge, of course, and this direction is normal to the edge. Then you create some block of your image, and then you compute histogram of these 2 magnitude and angle in these blocks of the image, and so on, till we get the final feature vector that has a specific form. This is implemented in MATLAB, in Python, so you don't need to know which are the steps. What is important is that when you get an image, you can represent your image with the OG features, and you can also display it. So these are the OG features for this image. You get, for example, a human model of what you are looking for. And when you get a convolution of the histogram-oriented gradient, the OG features, with your model, you get this representation, this final representation, that is the input of your classifier. So your classifier, instead of taking the first image of this lady as the input that is made, this is a rectangular matrix of many pixels, you get this very slight representation that is much more informative than the input image, and should decide if this is a human or not, considering just this representation of the image. And why this is important? Because this is invariant against illumination, scale, rotation, perspective. So it is very useful working with og features with images, in images. Or another possibility is the scale invariant feature transform. This is another feature extraction technique where you smartly create many representation of your image. How you create your representation? You take your input image and then you apply some blurring. Blurring means that you're using a convolutional filter with the Gaussian kernel. So for you that, as me, a problem with your eyes, is the same of taking your glassing off. So this is an image completely blurred. And this is the result of a convolution with a Gaussian filter. So you're making the image blur. Why you do like this? Because when you capture an image of a target that is in front of you, let's say of this mobile phone here, you are focusing on your mobile, and you're taking the best image you can. If you are blurring, is technically the same of putting your focus instead of your target, I don't know, 1 meter below your target. So you are saying that your camera is focusing at different depths. Okay, this is made because you want something that should be, of course, scale invariant, but also perspective invariant. So your mobile should be a mobile if you make your capture with the mobile here or with the mobile 10 meters farther from your point of view. So you are creating something artificially that is making a representation as the depth, the focus depth is changed with this Gaussian filter. And then, so this is the way we can contrast, we can make something perspective insensitive. But at the same time, we want something that is scale insensitive. This mobile should be a mobile if it is represented in 200 by 400 pixels, and the same for a mobile that is large, 20 pixels by 40 pixels. Okay, how we can do that? Creating different representation, different scales. So you make your blurring and then downscale the image and create another octave made of new representations. You can create many of these representations, of course. And when you make a subtraction, you get this difference of Gaussian, and try to find in this difference of Gaussians some key points that are point of high contrast. And there, make your feature vector of the location in pixel of your point. Then the level where the gradient is maximum or is minimum. The strength and orientation of the gradient sign, and so on. So this is another way of creating a feature that could be applied in any domain when you work, of course, with image processing. For example, let's say that you have a model of a shoe. You can extract from this model your SIFT features and then try to find the same displacement of your features within another image. And then try to correlate this information to find an object within an image. Or for image stitching. And this is actually what is done when you make a panorama picture with your phone. So you get multiple frames, and then these frames are aligned, are stitched, comparing features. So for example, the SIFT features of this mountain are this one and are again found in the second image till we get a point-by-point comparison, and then we can stitch the two images to get a wider image. Again, these are general purpose features, but in your case, you will define your own features, or even you can use some features like these ones that are valid almost everywhere in image processing. Okay. So a few words about unsupervised learning. So in unsupervised learning, we have already said that we have a data set, but we don't have the labels. This is a kind of problem that is also known as a knowledge discovery. So you are clustering your input data, and then with trying to understanding the process that you are looking, you will give a meaning to any of your clusters. For example, these are the input feature in a feature space, two-dimensional feature space. So my feature vector is in 2 dimensions, in 2 dimensions, so is a vector of 2 elements, nothing more than this. So we can make a scatter plot, and without knowing nothing at all of the problem, maybe we know that this is a cluster, this is another cluster. We can find 5 clusters of points. So maybe the easiest way to make clustering is the key means. So you typically select this number k of clusters and define some location in your feature space, in this case a 2D space, of your clusters. Then you will create a kind of separation made because you have placed this cluster here. The centroid of your cluster is placed here, so you get separation, and you will group all the points that are belonging to this area. For example, is an area of cluster 1. Then you estimate the new center of mass of your cluster and move your centroid to this position. So let's say that once you estimate, for example, here in this region on the top of the representation of the space, of the 2D space, you get that your center of mass of this point, instead of being here, is moved here. And then replicate until you get a convergence. So this is an example. So you are moving your points, and then you are assigning all the prediction, all the points to a specific cluster. Okay, for example, in the first frame they were all blue, so the blue cluster moves till top right, while red moves on the top and green moves on the right. Let's say something. If you change your input condition, of course, the clusters will change. Even the cluster will change. Let's say that I cannot stop it because this is a GIF image, but let's say that instead of having placed your blue dot here, this is red. So this at the end of your process, this cluster will be red. This one, I don't know, would be blue, and this one green. So anytime you change your initial conditions, you will get different clusters. So you get the same cluster, but with different meaning. And this is the reason why this is very sensitive to the initial points. Then there's another point. You should select manually the number of clusters that you want to get at the end of your clustering. And maybe you can, so in our case, let's say we will see something on MATLAB now. Let's say that you should have a classification of 3 classes. Okay, I will define this k as equal to 3. But maybe adding more values, more clusters, can also help you in the discrimination. And we'll see something now. So maybe 4 clusters where 2 clusters have the same meaning, for example, background, performs better than setting the 3 clusters, because you should take into account information that in 3 clusters are not representative. There's an important advantage that is very easy to be implemented. This is the easiest way to make some clustering. Another way is hierarchical clustering. This is something similar where you start from unlabeled points, and let's say that we are making an agglomerative approach, because also there's another approach that is completely the opposite. As long as you have your points, you can group 2 observations in one cluster. Let's say that we start here, that these 2 points are in this cluster. Then the closest points are these 2 ones, and we get another cluster. Again, these 2, now this point and this cluster are the closest, and we can merge them. Then this point and this cluster are the closest, and we can merge them. Then these 2 are the closest. Of course, there's nothing else than these 2 clusters, and merge everything in just one cluster. Why is it important? Because here we don't need to define how many clusters we want. Then, once we get this representation, we just cut our representation, let's say here, and say that I have for free 3 clusters. I can get 4, 5, how many clusters you want for free, because you have your representation, your hierarchical representation of the way examples are clustering together. Okay. For example, we get always in an agglomerative approach, 5 classes, then 3 classes, 2 classes, just 1 class. There are possible cuts that you can do. For example, let's say that you are using 2 classes. You want to, instead of repeating everything, you just say, okay, I want to cut here my dendrogram. This is the actual name. And then say the results just for 2 classes or 3 classes. Everything is for free. The dendrogram can also be represented like this. For example, E and F are the closest and are at the base of my dendrogram. A and B are the other closest and are at this level. Then you can cut your dendrogram, for example, here, for having just 2 clusters. These clusters are made of A and B and C, D, E, F. This is for free. There's also a divisive approach that is from one cluster. So we split, deleting from this cluster what is the most different example in the cluster, and making them 2 clusters and so on. But it's not really used. Typically, agglomerative approach is used. Again, there's no assumption on the number of clusters. You can cut your dendrogram wherever you want. And also, you can use hierarchical clustering and give some meaningful representation of your cut. It's something similar to decision tree, and we will see now what is a decision tree. So let's move to MATLAB. Oh, there's a question, I don't know. Let me check. Chat. 25. Okay, so this was a of 30 minutes ago, a question of 30 minutes ago. So is there any criteria to identify and gauge overfitting or underfitting? So underfitting is quite easy. If it doesn't work, you are underfitting, your model is underfitting. Overfitting is where, for example, you get a training result with very good accuracy, and your test has not a good accuracy as well. Make a measure of overfitting is something impossible. This is mainly driven by your experience. So once you have an outlook of the state of the art and you see a paper that get 99% of accuracy in testing, maybe they are making an overfitting on the test data that are too close to the training data. Okay, so that's the point. Depending on the problem, the numbers could change, of course, but 99% is something, let's say, impossible to reach. Okay, so now let's move to MATLAB. And just see a brief example of unsupervised clustering on the data that we have. I will go, let's say, fast through the code. But in any case, if you have questions, please stop me or discuss about it together. MATLAB, responding. Okay, unsupervised clustering. Okay, it is ready. So the data that I'm using here are taken from the glass fiber reinforced polymer, so the same specimen that we have seen before, and we have the ground truth. We know almost everything of this specimen. This is our polar star in this course. And we are using data from lock-in thermography. We are just using an input excitation with a sinusoidal wave with a period of 2 minutes. Okay. And as if you can remember, in lock-in thermography, instead of using the whole behavior of the temperature in time, you can compress all the information in an amplitude and phase map. And what I'm plotting here are the amplitude and phase maps, if it responds. Okay. These are the amplitude and phase maps of our specimen. Of course, our region of interest is just this one with the flat bottom. So in the amplitude, you can see the first line. In the phase map, you can see the first line as well, but also something from the second line. So phase, as I told you before, is more informative than the amplitude, typically in this kind of analysis. And even if you here have an image that is very well contrasted instead of the phase map. So how we can make our processing. So in this line, I just selected the region of interest. So I'm taking the amplitude values that range in X between these two values and along y-axis vertically of these two regions. So I'm taking just these lines and these columns from the amplitude and the phase. I will use only the phase, but I'm taking account also the amplitude. So then I'm creating here with this mesh grid, a grid with a sample step equal to 2, just so that you can also make it equal to 1, but just for to speed up the computation here, I will take it equal to 2. So these are the coordinates within the region of interest where I'll take my features. So for these x and y points, let me show you. I can display x and y grid, and these are the points, the couples of points, x and y coordinates, where I will find my features. So as I define a sample step equal to 2, so instead I have an x of 411, and here, let's say 177. The second one is 179, and the same is for x. I make a step from 411 to 413. Now, first of all, an image processing, very easy image processing. I will normalize the images because amplitude and phase. Phase could range between 0 and 2 pi. Instead, so our double data. So if I pick the element of the phase map, I will see the something that is in floating point notation. But images are between 0 and 255 in a sign chart. Okay, so I need to change my representation. Instead of having a domain for the phase between 0 and 2 pi, between 0 and 55, sorry. And then everything as an integer. So I'm just casting my variable to an integer, to an unsigned char, an integer of 8 bits. And then making an histogram equalization. This is a built-in function of MATLAB that is used for improving the contrast of your image. So once I don't know if you have ever played with some picture, you can improve the contrast of your picture by taking the histogram and spread it between 0 and 255. So for example, if you have that your image is almost completely bounded between, let's say, 100 and 120 values of your pixels, maybe you can spread it to use the whole dynamic range that you get in your unsigned chart, so between 0 and 255. And the results are in this plot. So these are the input images, and these are the representation with the best contrast that you can. So where, of course, it is 0, you will, or close to 0, this point should be shifted more at 0. Okay, so your minimum and maximum of phase should be 0 and 255, and the same for the amplitude. Here, for example, you are saturating the contribution of your or inside the flat bottom holes, but you are improving also the contrast in the flat region. Okay, so that's the result of histogram equalization. Then, once we have these maps, we can extract some feature. Let's say that we want to extract the SIFT feature. So instead of the SIFT, here I use the surf that are speeded up robust feature that has the same meaning of the SIFT, but there's a change in the algorithm to make it much faster than the one of the SIFT. But the meaning is the same that we have seen before. So I'm extracting from any point of the grid that I defined before the surf features using this other built-in function from MATLAB. And then, as I told you before, you can estimate your features wherever, but then these feature points are deleted from your set if the contrast is not too high. So it returns not only the features, but also the valid points where you are computing your features. Not all the points of the grid are valid. I can spoil you that all the points are valid for this formulation, but in some application, maybe it's not the truth. And I'm making for the amplitude map, equalized amplitude map, and for the equalized phase map. Okay, and my features are these ones. I can run it, and the size of my feature vectors is of SD. So my feature vector has this size, where these 21,000 points are the valid points where I am estimating the feature vectors, and 128 is the number, is the size, is the length of the feature vectors. So instead of representing a point with just a point with 2 points, so with the amplitude and phase, I'm considering a much higher representation. So instead of using for a single point the amplitude and the phase map, I'm using for a single point all the feature vector made of 64 for the amplitude and 64 elements for the phase map. Okay, so we say, but should this feature be lower than the input? So why are you using these feature maps instead of using the features as the amplitude and phase values as they are? Because features are taking into account also the contribution of the neighbors. Because as I told you before, I will take the amplitude, so I can take for just 1 point the amplitude and the phase that I detected for this point. But this is a punctual information. If I'm taking in this point, instead of the amplitude and the phase, the feature, the SIFT feature for that point from the amplitude map and the phase map, I'm also considering the neighbors of my points. So I'm adding much more information to my input, okay? Then I will create a classifier. So I have my data, my input data with this size. I have 21,000 examples, and my feature space is R at the power of 128. Okay, this is the dimensionality of my feature vector. So I want to use, for example, hierarchical clustering on these features. So these are functions that you can take from any tutorial of MATLAB. So the important is to get the principle of hierarchical clustering. Then how to implement it is very easy. So are actually 3 lines of code: this, and this one. So in 3 lines, you get your hierarchical clustering. The first line compute the Euclidean distance between all the points, all the examples, 21,000 examples in your data set. Okay, Euclidean distance in the space of 128 or 128 features. Okay, so you will get a 21,000 by 21,000 matrix, triangular matrix, where the diagonal is equal to 0, because of course the distance with myself is equal to 0. And then with the triangular symmetry, the other distances, Euclidean distances, computed in the space of the feature, in the feature space. Then you will say that I want to create the linkage structure, the dendrogram of your inputs, of your examples that you're representing in your data. Okay, and I can plot, for example, the dendrogram. So PDist takes a few seconds for the computation. It's not easy for my laptop. And this is the dendrogram representation. Okay, so of course there are 21,000 elements. It stops at 30 clusters, but you can make a cut, for example, here, and automatically have all the points that are in those groups. Then you just take here the magic number, how many clusters you want for your representation, let's say 4, and then construct your clusters. So here we don't have a training and a test set because we don't have labels. So there's no reason to make a training set and a test set. We are just grouping anything that we have inside our process. And at the end, with this plot, just a word. If I plot this number here, this vector here, this is made of these numbers are the clusters, so of any point that you have defined where you compute your features. If I may, for example, if I see that the number of elements of okay, so the number of elements is equal to 21,000. So any point where I compute my features has been classified. Okay, and this plot here show you the results of my classification. Maybe it's not the best plot I can show you. Let me change the marker size, say to 5. It again. Okay. So, can you see the color? Yes. So green, of course, maybe is sound region. Red is the boundary of the defect. Blue is inside the defect. This red here is the second line of the defect. So with unsupervised clustering, we have seen something also here, and there's something here in red again, and also here. So without any knowledge of the input, you have made a cluster and group points that are similar in the feature space. Okay. Now, just some post-processing. So before I said that instead of using this maximum number of clusters equal to 3, I decided to take it equal to 4, just to have to represent in 2 clusters the background region, which is the largest among the 3 classes. And maybe here you will get there's if I change this maximum number of clusters, and I can do that for you, to 3, and then compute again this, just this, not everything, because then I will comment this line and plot it again. So results are even good, but you don't have the capability, for example, to detect this point, because this point has been clustered as a background, or green has no meaning. So even in this case, green and blue are underlying the background, while only red is saying that there's a defect there. Okay. So go back with placing this like this, and then again. Points of cluster 3 will be set to 1, and points of cluster 1 will be set to 1. So I'm just detecting defects. So I'm grouping cluster 1 and cluster 3 and saying that they belong to one single class of defect. And then I'm deleting the results. So this is a morphological operation. So if you have, let's say, this image, this was a black and white image. Deletion means that you are adding, depending on this was not maybe the best image that I can. Let's say a line like this. And delete with a mask of 3 by 3 pixels, okay, like this. So if you add that this pixel is white, you are making all the pixel in the mask white. So you are somehow enlarging your shape, your silhouette. So at the end of the story, your line will be something like this. So you are enlarging, deleting, in terms of delete, delete, that's the word. Deleting your image. And this is the result. Okay. The first line, and may information about the edge of the first line and the second line. Then we can make also other processing, other image processing. For example, let me enlarge it. These are points. You can check if the area of the connected components is higher than a threshold. And then if it is higher, say that this is a defect. Or if it is below a threshold, remove this connected component from your final result. We can do that here. And we removed all the small pixels. So for class 2, for the second class. So we have already obtained that this is the best representation of the class of the defects in the second line, and of the edge that have the same, in our feature space, have the same behavior of the edges and of this element. This is the result of the unsupervised clustering. Even if we didn't have any information about our specimen, we will get this final result without any label. Then I am the expert of the domain, and I can say that these are defects or edges of the flat bottom holes. Okay, I'm discovering the knowledge. That's the point. Now, go back. It's late. and go back to supervised learning. Now we are using a labeled set of inputs. What does it mean? Sorry. That we can actually learn from something that we know from our dataset. There are many ways, of course, to realize supervised learning. Correct? This is just an example. In any case, you will define some objective function, some error function, and you want your model to optimize this objective function. Let's say a very simple example, a mail spamming algorithm. Let's say that you have the number of recipients of your mail, and you have your data set that is trained. Non-spam, spam. You can just make on this example, make a separation. For example, here, if the linear separation, if the number of recipients is lower than 1, this is not spam, but you are making black mistakes. Or you can set your threshold to 2, and then your error is this one, that is much lower than what you get before. So this means optimization of your cost function. Try to find the best, in this case it's easy, the best separation between your examples that are all labeled. Of course, there are many features that you can use. For example, the mail length, the number of recipients, and then you can create your separation like linear separation to separate what is good from what is not good. The easiest way is the nearest neighbor, because it is very easy to be implemented and easy to understand. So it's based on a voting mechanism, nothing more than this. So this is much easier. Once you get so let's say that we are focusing on this example here, the green cross. You say that your k is equal to 1, and this is something that you should set. If it is equal to 1, this example will be labeled. This is a test example will be labeled with the closest. Okay, because your k is equal to 1. Then you will set, for example, your key number equal to 2, and then say which are the examples in my feature space that are the 2 closest examples that I have, minus and plus. I will decide with minus just because this minus is closest, even closest to my cross. Okay. Then again, make this k equal to 3. I will pick the 3 examples of my training set that are the 3 closest, and then in the voting mechanism say that this new test is equal to plus, because 2 over 3 are plus examples of the training set. Okay. So, but the problem is how we can choose this value k. So should we take this low or high? Because if it is low, maybe it will be much more sensitive to noise. If it is too large, maybe you are taking into account the effects of clusters that are far from your actual observation of the phenomena that you are testing. In principle, this should be lower than the square root of the number of elements that you have in your training set. But as in many fields of machine learning, you should try and say what is the best k. But Matra, for example, did it for you. That's it for you, sorry. And we can have some improvements. For example, instead of using the direct distance, maybe you can make some weighted distance. So giving more weight to some specific feature that maybe is more representative of your problem. If the feature, let's say in the previous example, we get an array for any observation. For one observation, we get an array of 128 features. Maybe the fourth and the fifth features are the most informative, and you are giving them a weight. So in the voting mechanism, these fourth and fifth features will vote as 3 or 4 features. Okay, so you are giving more importance to this feature. Or you can also normalize the distance, because maybe, so we are always discussing about numbers. Maybe there's a feature that has a range between 0 and 1, and another feature that has a range between 0 and 1 million. Of course, this feature maybe, or even it is clear, that would be more important just because the magnitude, the number itself is much higher than the one of first feature. And maybe it is better to make a normalization of the whole vector in order to get a dynamic range bounded for all the features, for all the numbers of your feature vectors. Okay. Because we are working with distances. So, and we want to make the computation of this distance as fair as possible. Okay. There are many ways to compute these distances, Euclidean distance, Manolabis distance. I don't want to spend too many words about these distances. You can try your the best distance for your problem, depending on your problem, of course. Supported vector machine. Support vector machines are one of the most important classifiers that you can use in for classification of feature vectors. They are able to make a good generalization, and we will see why. Are very efficient, but just works. They work for binary classification. So in the theory, the classification is made between -1 and 1. So we are classifying binary problems. And if we want to extend to multi-class, that is possible for sure, you should create an approach, a one versus all approach. So consider, so create 10 models for 10 classes, where one model is created for taking that class as positive and all the remaining classes as negative. Okay, so this is the one versus all strategy. So in any case, you can use also some support vector machines. And in principle, you have your feature vectors, and you have the output of known labels, -1 or 1 in a binary classification. So the problem is to find some model parameter, this theta vector, so that the prediction is made by considering the sign function, and this is why -1 and 1, the result of a sign function of this product here, that is the inner dot product. So this means that theta, an element-wise product, and then the summation of the result. So we get just one scalar. And then taking the sign of this scalar of this number, you will decide if if a feature vector X in your test belongs to a class or to the other. Okay. And this product, this dot product equal to 0 is known as an hyperplane. Maybe with then we will see an example which is much clearer than what we can say in our analysis. So let's say that we have two classes, of course, because a binary problem, which is the best separator. Maybe these are all separators, but maybe the best is this one, because we are in, let's say, having a margin, a safety margin from both clusters, from both classes. What happens? So, but all are valid, of course, all are valid. What happens if we have noise? Let's say that so this is just a way to understand how support vector machines work. For example, instead of having a punctual value, let's say that you have something with an uncertainty, okay? Described by these circles. Of course, all the separators that belongs to this range of uncertainty are no longer valid, are no longer a good separator between the two classes. We can improve till we get the best of our separators. Increasing the noise, just one separator remains. This width is known as a margin, and we need to take this margin as wide as possible. Okay, just to have just one separator. Okay, of course, in this case, it is very easy problem, but you should think about a representation of feature vector in an n-dimensional space, where this is not a line, but is an hyperplane. Go back to the definition before, an hyperplane. Sorry. Let's say that we have x1 and x2, and this is our hyperplane, because our model, our best model, is made with theta equal to 1, 0. 1, 0, dot product x1, x2 means that I have at the end of the story just x1. Okay, so I'm taking x1 equal to 0, that is the x2 axis, as my separator. The margin is defined as the 2 over the 2 norm of theta, and is equal actually to 2 in this case. Okay, so just this obvious notation here. X2 has no meaning for this problem, so we can use this x2 just for representing the features, but actually if x1 is equal to 1 is hyperplane, means the x2 is not working for solving the problem at all. Just one feature is enough. So here we get a linearly separable problem. What happens if we have something like this? So there's not a separator like a line that can divide the two classes in binary classification, like in this case. Maybe you can use some function, let's say everything is squared, where you can have a linear separation. So this is just a way of representing your data and create a linearly separable problem. Okay, so you can apply all the theory of SVM also to non-linearly separable problems. Actually, this is known as the kernel trick. It's actually a trick. So instead of using the product here, instead of defining a function, you typically use, and of course you want to create, so let's say that xi and xj are theta and x. So instead of computing passing the input to the phi functions and then computing the dot product, you define a kernel that, for example, a Gaussian kernel that is defined in this way. So you are creating from a problem, you are applying something that is not linear in a kernel trick. And this kernel trick is done also for reducing the computational cost of your problem. Because maybe take your input, apply your function, and then the dot product between them is much more expensive than just computing the Gaussian of the difference of your input vectors. Okay. And that's the point for multi-class classification. That's something that we already discussed. So instead of having just one theta, you will get as many theta and as your classes are in number. Okay, so 10 classes, 10 models. The decision trees. So in decision trees, the idea is very easy. Try to answer to a sequence of questions. Okay. And you define the best attributes for any node, and then you split between two branches, and then again other branches, till we get the leaves of our tree, and every single leaf is a class or related to a class. Maybe it is better to get an example. Let's say that we want to solve this problem. When somebody can play tennis, these are our predictors, and this is the response. Yes or no, this is the response. Binary classification. Our predictors in this case are categorical. So just take a look. It's raining, it's sunny, it's whatever. The temperature, hot, cold. Humidity, high, normal. So these are the inputs. A single line is an instance of our training set. If it's raining, it's cool, humidity is normal, and wind is very strong, they don't play. Okay, so this is the expected response. So the idea is to create a sequence of questions as low as possible in number of questions to get the final answer. For example, take a look. Is sunny, overcast, or rain? If it is sorry, go back. Every time overcast, yes. Okay, so I just have a classification. If it is sunny, let's check the humidity. Is it high or is it normal? If it is high, it's better not to play. If it is normal, let's go playing. The same is raining. Okay, but let me check the wind. If it is strong or weak. Maybe this is weak, we can play, or if it's not, the wind is strong, it's better to stay at home. Of course, strong, weak, high, normal are categorical attributes, but instead of using categorical attributes, this is a very simple example, we can also have numbers. Is the humidity higher than 75%? Okay, if so, maybe it's better not to play. It's better not, it's better yes. So we are even using numerical attributes. A decision tree makes a decision boundary. The decision boundary is something like this. So in this case, we can represent because my feature space is two-dimensional. And there's a decision boundary, for example, x2 less than 3. So we can split the two conditions. x2, so this is the line, okay? And now I'm just considering this region. x1 lesser than 4, 0, higher than 4, 1. Now, go on the top. So for values of x2 higher than 3. higher or equal than 3. If x1 is higher than 3, I can always decide for 1. Okay. Then the rest of the region, the decision is made on x2. Is x2 lower than 4? Okay, decide for 0. If higher, decide for 1. Okay, my decision boundary is this green line, this green segment. Of course, you can use decision trees not only for binary problems, but for any multi-class classification problem. So the point is, how can I select the attributes? Which are the best attributes that we can use for making the splitting? For example, let's say that we have these two clusters, these two classes. I don't know which are the meaning of these classes. And then we can make a split, for example, in my tree, in a node of my tree, I'm in this at this point, and say that the splitting is between less or equal to 50,000, I don't know, it's a balance, euros, or higher than 50,000 euros. In this case, is he unemployed or employed? Maybe this splitting is much more informative than this one, because in this case I can fall in a direct classification, green and pink. Okay, so we should always have the attributes that are able to gain more and more in terms of information. Also, in this case, there's a problem of overfitting. So you can define the best tree ever, made of 10,000 of leaves for solving a binary problem. But maybe this is too complex for solving your problem. So you will get, even in this case, overfitting, because any other example of the test could be driven, the decision, the prediction could be driven by the training set. It's not capable of generalizing everything. And so at the end of the story, you don't have a good accuracy in your test. So the solution is to, for example, there are two solutions. Stop growing the tree earlier, so just the training before the convergence, the actual convergence, or training everything till the convergence and then prune the tree. So select the point where I delayed some leaves from my tree. Applications. It is very, very useful for, let's say, in this case, the diagnosis of, say, breast cancer. For example, a sequence of questions. Your parents have suffered from cancer? Yes or no? And you can split. If not, maybe there's not a problem with genetics. Let's say. So there's a meaning for any of the questions that you have in any node of your tree. And for example, the classification made by humans was of 65%. The decision tree made a correctness of 72. These are results of 20 years ago. Not 20, sorry, 10 years ago. British Petroleum designed the decision tree for separation of short platforms, as designed for a plane flight controller, and also the first release of the body tracking library from Microsoft, by Microsoft, implemented decision trees. So the scanning body tracking means that once you get a representation of somebody in a 3D space or even in images, you're able to detect the joints of people. okay, of the person that is in front of you. And this result was obtained. We are talking about the earliest 2011, 2012, were made using decision trees. Okay, where the input features were geometrical features, so the distances of adjacent points, because the Kinect, if you can remember, the first is a camera able to produce also the 3D shape of the target. Neural networks. Maybe neural networks is something that you have seen before. I don't know. No? Okay. I'll go that later. So the basic idea is to create an artificial neural network that is able to resemble our way of thinking, our biological neural network. These were designed for the first time in the 60s with the perception, what we've seen at the beginning of this lecture. Then there was a lot of research in this topic, and the basic idea is to replicate a biological. In a biological neuron, you get some dendrites that is receiving information from means in this case electrical signals from other neurons. Then there's a processing unit that makes some linear operation on the electrical pulse that have been received from your previous neurons, and then create a response through the axon and through the synapses to the other neurons. So there's a network, a net of neurons that are linked by dendrites and axons. And between a dendrite and an axon, there's a synapse that is performing a weighting of the electrical signals. So you are producing an electrical signal of, I don't know, let's say an example of 2 picovolts, let's say in magnitude, and you are weighting it by your synapse that is working to change these electrical signals to something that is different. Instead of 2, you get 1 picovolts as input of the next neuron. If you are completely drunk, your synapse will make more weighting, and so you will be, let's say, happier than before. So in an artificial neural network, the soma is the node. So where the operations are running. The inputs are the dendrites, synapses are ways or interconnections, and the output is the axon. There are many differences, of course. Biological neural network are massively parallel. In neural network, you can also implement a kind of parallelism, but not the same of our brain, surely. In artificial neural network, there's a slight tolerance to alteration of the inputs. So, because everything should be well formatted as expected. For example, you define your feature. So typically you expect that something as an input should be in your brain. Maybe you can also start reasoning with something that you had never seen before. Okay. Fault tolerance, there's a robust resiliency in artificial neural network. Unfortunately, it's not the same for biological neural network. If you have problems, if I have problems with my brain, I cannot go on with reasoning and so on. And for storage capability, you will implement some memory locations in artificial neural network, something that is different from the biological neural network. So this is the principle. So everything is weighted, then summed in your body, in the body of the neuron, in the soma. And then there's a threshold that is activating that specific neuron that now produce something as an output. That is the input for the next one. Okay. And it's almost the same in an artificial neural network, where you get a summation of inputs that are weighted by some weights that are found during the training. So when you define your architecture means that you are making, okay, a layer of 10 neurons that are accepting the inputs. Then another layer of 100 neurons, and then a third layer, an output layer of, you have 3 classes, 3 neurons. And the output of these last 3 neurons are the probability that the input that you have proposed to your network belongs to a specific class. Okay, you are defining. So what I've done in this last 30 seconds is defining the architecture, but everything is equal to 0. So you need to give your input for training in order to get these the values of your weights and your bias, because typically you add the bias, this B term, to any of your neuron. Then there's a threshold, because that means that you're activating or not your neuron, and you produce an output that is for the next neuron. And the activation function is that in this case was just a threshold. So if the output of this summation is higher than 0, the output is 1. If it's lower or equal to 0, the output is 0. This activation function is important because if you don't have it, you maybe can diverge in your network, because you are summing, and summing. At the end of the story, you will get some number that could be of trillions in terms of number. Okay, so you need some activation just to take bounded these values. Okay, and it's the same that we make in our brain. Okay, this could be a threshold or some function. Let's say this function that has a shape, an S-shaped function, but there are many other possibilities for the activation, and we will see them in the next lecture. This is the architecture. Let's say that here we are solving a binary problem, so we get just 2 neurons at the end, and this is always like this. These are the inputs, so the input layer in artificial neural network as the ones that era vigilante. Artificial neural network proposed till 2010, let's say 2011, where had just these 3 layers: an input layer, an hidden layer, and an output layer. The number of output neurons is always equal to the number of classes that you want to classify. The number of input, whatever you want. The number of hidden layer, whatever you want. So the input feature vector is given to your input layer, then is processed to the hidden layer, and then to the output. At the end here, you get a bounded value that is between 0 and 1, and is, let's say that this neuron is classifying class 0. This is the probability that your input feature vectors belong to class 0. This is for class 1. This should be the probability that your input feature vectors, the feature vector belongs to class 1. Okay. In this case, this is a fully connected, so it is not always like this. Maybe you can get that this input in your, when you define your architecture, maybe you want that this neuron, for example, can communicate, is linked just to the first 3 neurons and not to these ones. I don't know why, but it's possible also to impose it. But when it is fully connected, you can define a matrix form, this structure in a matrix form, and we will see it in the next lecture. You can solve many problems, or even nonlinear problems. That these are implemented in many applications, for example, for function approximation, regression analysis. So, for example, you have a time series of a signal that, let's say, is the temperature during the day. You can use your training of the last 10 days and then ask, for example, let's say that today I have this temperature at 10 o'clock, which is the temperature at 11 o'clock, and this is a problem of function approximation. So they are capable of predicting somehow, I don't know why, I don't know how, but with the model that they have learned, are able to predict the next value of the temperature. Okay. The problem, the number of hidden units has to be tuned. So there's not the recipe to say, okay, I want 100 hidden units for my problem. Because if you have a number of hidden units that is too low, you are underfitting. If you have that this number is too high, you are overfitting. It's always the same story. And there's a slight control over what the network is doing during classification. So actually, today, we don't know how our brain is reasoning. So there's no way to understand. So we typically know that memory is in a specific part of our brain, but actually, we don't know which are the mechanisms that makes us remember some date or the content of this lecture. We don't know, actually. And it's the same for artificial neural network. We don't know at the end of the training what they are doing, but they do. They do something and possibly it works. Now, in this last, so is there any question? Any other question? Okay. Just this 30 minutes. An example of the supervised learning on our data. Okay. Let's start. So I divided this problem into codes. The first one is a code for feature extraction. So try to understand from our temperature signals, instead of using standard features as we had done before, try to use something that is tailored by me, that I'm the expert of the domain, and then classify only these features instead of using, for example, the whole temperature signal. I'm taking this data. You will find on the website, there's everything. So if you want to replicate these results, you can do it. These are the results from step Eaton thermography, and that we have produced in the last lecture, in lecture 4. So we are working again with the glass fiber fused polymer specimen, our polar star, and in step Eaton thermography means that we are using those video sequences that we've seen before, where we are exciting for 225 seconds the specimen, and then taking the cooling phase and try to understand from this signal if there's a defect within the material. So I just loaded the data. So in my workspace, I got this video sequence. This is a structure where then there are the 3D metrics that are the videos of my temperature maps. Now, I want to isolate just the cooling regime. So what I'm doing here is for all the pixels, try to understand where the pixel is maximum in time because this is the third dimension in my max function. This is the position, the frame position, where my signal is maximum, because I think that at this point should start my cooling regime, because I'm switching off the lights. Then I will create, so even if I'm switching off the lights in this moment, maybe there's a point that is, because your source is not homogeneous on the whole surface, maybe there's a point that is seeing this switching off few milliseconds later than the point that is much closer to the surface, to the sources. This means that here I'm averaging all the maximum points in time. So for example, let's say that one point has a maximum in frame number 100, and then the other point 101. Maybe it is better to make an average and say that the perfect point where I switch off the light was 1000.5. Okay, the average between the two values that I see. Of course, 0.5 has no meaning. I'm making a sale, so I'm rounding to the first integer. So instead of 1000.5, 100.5, 101 will be my maximum. So the frame where is the maximum, so where I switch off the lamps. Okay, the maximum temperature. And then I'm just isolating. So all the frames starting from this point till the end of the signal. Okay. And if you carry on, so just I want to plot it. I'm taking a point in 100, 100. So in pixel coordinate, 100, 100. It is working. Oh no, it's loading again. Then okay, never mind. Should be easy. So loading the data takes some time. Okay, so this is the cooling regime. If you can remember, somebody was working in the laboratory, and there was a discontinuity here. How we can manage it? So I just place in this plot, okay, like this, these points that are the position where there was this discontinuity in the temperature. I just picked it by hand. Now, I want to remove it, okay? And how can I do that? Let's say the time instant where there's this discontinuity are placed at 4, 22, and 13, 24, okay? These are the positions of my discontinuity in the temperatures. I will take in a for loop of just 2 cycles the first discontinuity, and then take the 30 temperature samples before my discontinuity. And with a very important approximation, say that in these 30 samples of temperature, the temperature was decaying linearly. Okay, so what does it mean? That the next temperature sample that is that has my discontinuity in this up actually should be lower and should follow the profile, the linear profile fitted on the average linear profile on the previous 30 samples. That's what I'm doing here. And then recompute it with this approximation, having it's very fast today. Okay, so this was what we had before, and now with this approximation, I'm here trying to to make everything, let's say, without any discontinuity. Of course, this is an approximation, but it works for us. Now, here I'm just making my normalization of the temperature, because as you can remember, instead of having temperature, whatever temperature we can have, we want to normalize it between 0 and 1 to be, let's say, insensitive to the laboratory conditions, to the temperature, the room temperature that you get in the specific time. Then in thermography, typically, instead of using the direct temperature measurement, you use a temperature contrast. So you take the temperature, the expected temperature from a sound region, and then make a subtraction with what you actually have on your surface. Why? Because if you go back to the thermal, to the theory, say if I have here, no, sorry. If we go back to the theory of our lecture, temperature was T0, the temperature where everything is homogeneous, plus something that is related to the resonance of my, due to the discontinuity. If I subtract T0, that is the temperature behavior that we get in sound condition where everything is homogeneous, I'm just focusing on the time contrast that maybe is 0 if, of course, there's nothing inside, or as some shape due to the presence of any discontinuity below the surface. So I have to, I must reconstruct the expected region from my panel, from my specimen. How I can do that? Let's say, so we know that the calibrated specimen has some line on the top and on the bottom has some lines, but we are not able to touch with thermography these lines. So I will take these last lines of my specimen and say that the expected temperature response of the structure should be the one that I see there, because there's no defect outside. I'm assuming that this region is a region of a sound region. Just a brief note about this. In any production line, typically your defects should be much lower in number than the region, the sound region. Maybe you can use your old data set and then, for example, derive your median, in my case, temperature, and say that this median temperature is the one of a sound region, because even if you get some defect, the shape of this defect is much lower than the whole background that you are having in your data set. Okay, so this is something that is applicable. We are not saying nothing more than assuming that my production line is making something that is typically good, and sometimes 0.1% of my goods have some flow. Okay, so we are making an hypothesis that is valid, is realistic. And I can create my temperature contrast by subtracting the normalized temperature before minus the expected temperature of a sound region. And this is the result. Okay. So let me open better this graph. We know where the effects are. So this is the sound, this in red, the sound expected temperature, well, the expected temperature of a sound region. And if I compute the temperature contrast from a sound region, is almost equal to 0. This is just noise. Okay, so we are using a good approximation with this median representation of the expected signal. And then we know where defects are, and we have done it when we created our ground truth the past lecture. And I can plot you, for example, the contrast that we get, the temperature contrast, depending on the defect. I just pick the temperature inside any defect of our 10 defects that we get in our. So this should be 0, because it's a temperature contrast, if there's no defect. But actually, because of the defects, there's a difference in this behavior, in this contrast. Okay, and when you get surface defects, for example, this one, which corresponds to a surface defect, you get that your temperature contrast is falling down and then go back to something that is equal to 0 in time. And if you have an in-depth defect, something inside, like this profile here, that is the largest in-depth defect, the first one with the biggest diameter of the second line, you get that your temperature contrast rises and then go back to 0. Okay, so these are the signals of temperature contrast. We want to create a feature representation of these signals. We don't need to take all 1,600 samples inside our classifier. Maybe we can reduce the dimensionality of these signals and give it to our classifier. Okay. How we can do that? For example, creating a model. If I define a model like this one, that maybe it's better to write down here. Okay. So A1 x squared plus A2 x, everything multiplied by e at the power of A3 x. Okay, where x actually is time. Okay, so I'm creating a model that I'm defining that is able to represent the behaviors that you have seen before. Okay, my parameters A1, A2, and A3 should be, of course, defined for all the signals. And then these are the inputs of my 3x1 feature vectors. Actually 1x3 feature vector. Okay. So I'm taking 1,600 samples and I'm representing all this signal, all the samples, in 3 parameters. This is feature reduction. Okay. I can plot it. This is a model where I, let's say, use, for example, all equal to 0, A equal to 1, 0.02, minus 0.5, 0.5, 0.02. I can plot it. And this is the profile that somehow can represent the contrast. So in blue should be contrast equal to 0. That means that is the sun region. This green one is probably related to a region of a surface defect. And this red here is probably a region of in-depth defect, something that is inside. All are equal to 0 where time is higher. Of course, the problem is now defining the elements of the vector A. And I can easily do this just using this function, LSQ curve fit. So I'm giving to MATLAB the model and then the actual values, time and temperature of values, and then MATLAB works for me for detecting the best 3 values of A that are able to create the best fit in terms of non-linear least square. Okay. And so here I use a par 4. So I'm using parallel computation of my laptop, but unfortunately this takes 4 hours. So I just save the results. I will load it for you and plot it. So these are the same input signals that we have seen before, and these are the signals represented by my model. So I'm creating a feature vector of 3 elements in a 3D space, and all the new data that I will put inside my network, my model, my classifier, should be displayed in this 3D model made by my features. Okay. And now I can also reshape everything and show you the 3 features that I obtained from my surface map. Okay, from my temperatures. So for every single pixel is a temperature. Every temperature is 3 features. Okay, and I'm then reshaping everything to plot feature A1, the coefficient of t squared, in here in the map for every single pixel. I'm just reshaping everything to plot you the images. So instead of having a whole video of 1,600 frames, I'm having 3 images. Okay, is almost the same of lock-in thermography. Instead of having the whole video lock-in thermography, I have just the amplitude and phase map that are, let's say, features for that problem. In my case, I got 3 features that are my best representation on my analytical problem. For example, A1 maybe is the best feature to identify defects of class 2. A2 is the best feature to classify defects of the first line. A3 maybe can help me in identifying the smallest diameters. Of course, they should work together for creating the final classification. So now I have just 5 minutes to show you that I will take these features as input for classifiers. Okay, so for every single pixel, I have 3 features. Now, let's move briefly here. Again, I will load the data, the same features that we already seen. I will divide the data set. As I told you before, the first thing to do is divide the data set to have an area of test and an area for the training of the network, right? How can I divide here? For example, I closed it. If it's too late, we can go on in the next lecture. But if you want, we can take just 10 minutes, 15 minutes to complete the lecture. It's up to you. If you have problems, trains, or... Okay. I will be... In our data set, we get something like this, right? Okay. I will take a region, an internal region here. I will take this region and use it for test. The other two regions will be used for training. Okay, that's the point. So I just removing completely this here, this line, this column of defects, and use it for testing then my classifiers. The other two regions will be used for training the data set, the model. And then, so where it is yellow is the training set. Where it is blue, this is the test set. These are pixels of the test set. So all the temperature belonging to the region will be used for testing the model. All the temperature from yellow regions for training the models. Now, there's an important point here. Is very, very important. If I display you the numbers of examples in training, you will see that class 0, which is the background, has 33,000 of examples. Instead, class 1 has just 650 examples. So there's a very important unbalancement between class 0, the background, and class 1 and class 2. Maybe if I take this data set as it is and say to the classifier, try to decide, maybe it will be, it will decide everywhere, every time for class 0, just because he had many examples of class 0 and few examples of class 1 and class 2. I will say, okay, instead of taking 83,000 examples of class 0, I will take this number equal to 652. So to get everything on the same level. But actually, there's more background than defect. And we should take into account it. So the strategy here is to take the points of class 0 and randomly, perfectly randomly, select a number of signals that is 10 times 652. So 6,520 examples of class 0. So my data set would be unbalanced yet, but it's unbalanced because there's a physical meaning. So because there's more background than defect. And that's what I do here. So with this random permutation, I'm just selecting 10 times the cardinality of class 1 points from the ground truth, from where the ground truth is equal to 0. Okay. At the end, we get that the number of examples of class 0 is equal to 6,520, and then 1/10 the other classes. Now, with MATLAB, there's a classification learner app that is very easy to be used. So the most important thing for you when you come back home is that you should take your brain and try to have the best features that you can have for model your problem. Then the classification. Train a classifier is the easiest thing. You should use, for example, this classification learner that is here. If you go here in the apps tab, you open here, and there's here a classification learner tool. You should open it, and with is on time, it should display a very fantastic window in 30 minutes. Okay, so there's start a new session. There's a wizard here. So you start a new session. I press, okay. And then from your data set, you just select the input. My input, I call it, is a train balanced. Okay, this is my input. A matrix of 7,824 samples, examples that are 652, 652, and 6,000, and yeah. So the summation is this number by three features. Okay, this is my training set. Okay, then my responses is this vector. So this vector here, GT train balanced, is made of the numbers 0, 1, 2. Okay, the expected class. Then you can set your cross-validation. Go back 2 hours ago, cross-validation scheme, how you want to change your K to make the best, to make everything insensitive to the way you select your test, your validation set. Let's say 5, and then start the session. It will input everything, load everything from your workspace. And you can also see this scatter plot. For example, if it works, these are in 2D space. The elements of the first feature, the elements of the second feature, and then the color is the class. You can also change your, this is just to, for example, if I plot column 1 and column 3, there's no way to understand if there's something different from the background. But if I plot column 2 and column 3, maybe there's just one difference here, one difference here. But of course, a classifier will take the 3 features as a whole and then decide, classify everything with respect to these 3 features. Then you can select here which classifier you want to train with your data. Okay, let's say that, for example, I want to classify a fine tree. That was already, let me limit this one. Let me check this. So maximum number of space. So there are many criteria that you can impose, but not going into details. We can just train. Press play and train. It's training. Okay. Now it will open some. I don't know if it will take long. Hopefully not. It start training my tree, and in hopefully few seconds should give me the accuracy of my validation, okay, and the confusion matrix for my training set. Confusion matrix is the one that we've seen before, where there are on the column the expected class, and on the lines, on the rows, the true classes. My accuracy was on 97%. So here we are discussing about training, non-testing, training. So on the validation set, we get an accuracy of 97%. this is the confusion matrix. So I can easily see that my model is able to get good results, and I just have one error, for example, so I expected class 2, but I decided for class 1. 88 times I expected class 2, but I unfortunately decided for class 0. But 500 times I expected class 2, and I actually get class 2. Okay, in training. I run, okay, sorry. Here, there's a way to export your model and to get this model into your workspace. I just don't save nothing because I run many predictors. You can do many examples, SVM, ensembles, naive Bayes classifier, linear discriminant, many examples, up to 32 classifiers you can train with MATLAB for free. It's something very easy. Just press play and you go. I make this for you. These are the classification, and now I make a prediction on the test set. Now I'm making prediction on the test. There is something that the model has never seen before. Okay, and these are the results. Okay, for some classifiers. This is the first one. The first plot is the ground truth. What I expected. SVM with cubic kernel, go back to the kernel trick, didn't work at all. So for him, it was everything of class. I don't know which class is that one. Everything was of class 2. The best recall ever, but precision equal to 0 for class 2. For the other, if you see here, there's a good of SVM linear with the linear kernel was not working for class 2. It's not detected. But all the others were more or less able to detect the 2 defects and to classify them. That's the point. Classify the defects. And if you see, there's also some points, there are also some points here where there was the third line of flat bottom also. Even if I didn't give this class, this fourth class to my model in the training, he was able to say, maybe there's something there. So so here, I am the expert of machine learning. I see this result and I would say, surely, maybe it's better to make a new ground truth with another class of defect and give this ground truth to my training and say, so start training with something more complex. And then we will see the results if you are able to detect even this kind of defects. That's the point of this loop that I showed you before. So imagine which are the features. Start thinking at the domain, and then once you get your results, say, how can I improve it? Maybe there's something that I can do, and go back to the data, and again define a new ground truth with some new thing, for example, new class or another way of defining my balancement of the training set. That will be another point, for example. Okay, and now I can also show you compute the accuracy, precision, recall, intersection over union, whatever, for the test. Let's say just the last one. A neural network, a wide neural network, so this means with a high number of hidden units, has a test accuracy on 99.1%. Okay, and you should say, well, but 15 minutes ago you said that 99% is something. Okay, you're right. Why? Because I'm taking a test set from the same sample that I'm using for the training. So at the end of this lecture, you discover something that is unfair. So typically, if you want to publish your results, you should take new data, actually new data, okay? Not taking some parts, because maybe you are predicting something. So you, in this case, you will take advantage of overfitting. If you have overfitting, maybe you can get 99%, okay? So that's the point. Maybe it is better to have another acquisition, even on the same sample, but different acquisition, and stay and try to test it with something different, okay? 10 minutes later, but I started 10 minutes late, so it's perfect, 3 hours. Okay. So if you have any question, it's time for you to raise your hand. Any question here? Everything crystal clear, right? Even for you? Ora la puoi fare la domanda.
Non ho ben capito quando cioè in che modo sono stati etichettati i vari segnali.
In che senso?
Cioè nel momento in cui ha plottato l'immagine dei vari segnali con il label difetto di superficie.
Ah, ok. Torniamo indietro.
Cioè, in che modo è stato dato l'informazione che quel segnale corrisponde al difetto di superficie? Non so se sono sempre chiaro.
È chiarissimo. È stata data dal fatto che io sapevo che stava lì il difetto.
E come gliel'abbiamo detto?
Abbiamo creato un ground truth che abbiamo fatto la volta scorsa, che era pieno di zeri dove c'era il background. 1, certo, è sequenziale. Gliel'abbiamo detto ieri, mercoledì,
Sì, okay.
che ci sono, infatti, quando, so the question is, when where I'm defining the ground truth, the ground truth is defined, okay, so let me skip this, is defined here. So in lecture 4, at the end of my lecture, we defined the ground truth. So when I open, okay, let me, so the workspace is completely clear. I'm just loading this MATLAB file, and I have my ground truth. If I make image scale of GT, this is the same that we have done in lecture 4. So I know, and if I plot, so size of GT is this one. So I will make, I will flatten everything of my GT. So I will take GT like this. I have these examples in my dataset, one for each pixel of the temperature map. And if I display this GT, of course, it almost everywhere equal to 0, but somewhere there are 650 ones and 650 twos. Okay. I don't know where, but somewhere there are. So the ground truth is something that you have because you are making supervised learning. So you have the labels. Ok.
Solo perché il passaggio non l'abbiamo fatto oggi, quindi pensavo insomma di averlo perso io.
Ok, no. Quello è il punto di partenza perché lo useremo anche alla prossima.
Che è già etichettato.
È già etichettato, quindi c'è tutto. Vabbè. Any other question? If so, I will stop recording and wish you a good weekend. Bye.
Thank you so much. Bye-bye.
Thank you. Bye. Stop.
Quindi la prossima